Okay, as far as the material in the gas transport area and what's going to be on your test, this video probably has more things on the test than all the others, but you still need to know the others, but really pay attention to what we're going to talk about here, because we're going to talk about oxygen loading and carbon dioxide unloading. And of course, when we say loading and unloading, we're saying from the blood, but we're going to say what actually happens to oxygen once it enters the blood, what actually happens to carbon dioxide once it enters the blood and once it leaves the blood. Okay, in the previous video, we said that oxygen in the alveolus, 1.5% of it just dissolves in the plasma, 98.5% of it goes into the red blood cell, and that is actually binding to the hemoglobin. And that was two things, and there are chemical equations that show that we'll talk about in a few minutes. But now the question is, what is it that carbon dioxide does once it loads into the blood? Well, it, instead of just doing two things, does three things. But the first thing, or one of the things it does, is 7% of all the carbon dioxide that goes into the blood dissolves in the plasma. Okay, now again, 7% of it dissolves in plasma. We're only 1.5% of oxygen dissolved in the plasma. And so we can think, well, there's more of this. Well, it makes sense because remember, carbon dioxide is always more soluble than oxygen is, so a higher percentage will dissolve directly in the plasma. But what happens to the other 93%? Well, the other 93% actually also go into a red blood cell. 23% of that 93% actually combines with hemoglobin, so it's going to stay in the red blood cell. But 70% is going to go into the red blood cell. It's going to be converted into what's called bicarbonate ions, and then it's going to leave, and the bicarbonate ions are actually going to go into the plasma, and they are a base, so they're going to make the blood slightly alkaline or basic. Now we're going to show the chemical equations for this, and then these chemical equations, in particularly what's going on here, it really helps explain a lot of things going on in the body. And first thing I want to say is all these equations will be reversible reactions, which I will show you in a minute. Okay, now again, 7% of carbon dioxide just went straight into the blood plasma from the cells and just stayed dissolved in the blood plasma. But 23% went into a red blood cell. Okay, it joined with hemoglobin, because and here there was a high partial pressure of carbon dioxide, and it was converted into what's called carbaminohemoglobin, which is HbCO2, and it just stays bound to the hemoglobin. Now, it doesn't bind to the exact area that the oxygen binds to, but oxygen has to be given off before the hemoglobin can bind to it. So when oxygen from the hemoglobin starts being given off, it actually makes room for the carbon dioxide to come in and bind to the hemoglobin, even though it doesn't bind to the iron portion of it. So it loaded into the blood at the tissues, because it was at the tissues where the cells were giving off the carbon dioxide. It's going to unload from the blood in the lungs, carbon dioxide is. So it is a reversible reaction. The carbaminohemoglobin will reverse, especially when oxygen starts coming in. It will reverse, and it will then dissociate into the hemoglobin and carbon dioxide. Now the carbon dioxide has the ability to leave. The hemoglobin now is opened up to receive oxygen that will be coming in at the lungs. Okay, so 5% of the carbon dioxide, 7% of carbon dioxide went directly and dissolved in the plasma. 23% went into the red blood cell, joined hemoglobin, became carbaminohemoglobin, and again, it was a reversible reaction. So where does the majority of of carbon dioxide, what does the majority of it do? Well, the majority of it, the 70%, goes from the cell into the plasma, into the red blood cell, and then there is an enzyme called carbonic anhydrase that puts it together with water. Now notice, carbon dioxide plus water, here's our enzyme that makes this able to happen, because we have our two binding sites, lowers the energy of activation, and we literally form something called carbonic acid right here. Now what do acids do? They give off protons, hydrogen ions. So if the carbonic acid gives off the proton, then what we have left over is we have a product called bicarbonate ion. So this was an acid, but when it gives off its proton, it turns into a base, bicarbonate ion. Well, the bicarbonate ion doesn't stay in the red blood cell, but instead it actually leaves and goes into the plasma. It does something called a chloride shift. Now, this carbonic acid, when it breaks into a proton and bicarbonate ion, the proton actually goes and joins with hemoglobin that's given up its oxygen. Now remember, when we're at the tissues, then the red blood cells are going to start, according to how low the partial pressure of oxygen is in the tissues, it's going to start giving off that oxygen. So the hemoglobin, which was carrying that oxygen, is now going to be open to receive other things. Well, we said earlier, one thing it can receive is carbon dioxide and form carbaminohemoglobin. But the other thing the hemoglobin can receive is this proton right here from the breakdown of the carbonic acid. Okay, so we call this reduced hemoglobin. Well, what's left over then is this base here, this bicarbonate ion. Okay, this base, which is negatively charged, leaves the red blood cell, but because it is negatively charged, when it leaves, it's replaced by another negatively charged ion, because we're trying to maintain that neutrality inside the cell. So if something negative leaves, something negative has to come in. We call this the chloride shift, because we lose this, goes into the blood. Now keep in mind, bicarbonate ion is the same thing that is released from the pancreas to neutralize the chyme, that very acidic product coming from the stomach acid. So we know it is a base. Well, when the bicarbonate ion, which is where 70% of this carbon dioxide is now, leaves the red blood cell, then it makes our blood have a pH of about 7.35 to 7.45, which is slightly alkaline, which then helps protect it from the lactic acid that may be being poured into it. Okay, now, so anyway, our bicarbonate ion now stays in the plasma until we get to the lungs. Okay, now we're in the lungs. Okay, so the reduced hemoglobin is still there. The chloride ion is still there. Our bicarbonate ion is out here. But since this is a reversible reaction, in the tissues we started this direction, but now that we're in the lungs, what's going to happen is the bicarbonate ion has got to come back into the cell, trade places with the chloride ion, so we say it's a chloride shift again. Once it's inside, then the proton will be given up as oxygen starts coming in. Okay, when that proton's given up, now it's free to join back with the bicarbonate ion that comes in. Then it becomes carbonic acid again. Our enzyme helps break it down. Now we have water and carbon dioxide. Now carbon dioxide can leave. We can exhale it. We see our bicarbonate ion has come back in, so now we see our chloride is leaving. Okay, diffuse back in, chloride is gone. But now it can't stay in this form, so it has to join with this proton. So this proton can join back with the bicarbonate ion to become carbonic acid again. Okay, once this gives up the proton, it joins, forms carbonic acid, then carbonic acid then is broken down into the water and the carbon dioxide. The water, of course, is going to stay in the cell, since cells are mostly water. The carbon dioxide then will leave and be exhaled. Okay, so we are in the lungs. So loading and unloading take place both in the lungs and the tissues, but remember, it's always from the perspective of the blood. What is loading into the blood at the lungs? Well, oxygen is. So what would be unloading from the blood in the lungs? Well, carbon dioxide would. Well, when oxygen does load into the lung, we know only about 1.5% actually goes directly into the plasma and stays saturated in the plasma, or dissolves in the plasma, and then 98.5% of oxygen going in goes in. It actually triggers the reduced hemoglobin to give up that proton, and now if that hemoglobin gives up the proton, now it can bond to the oxygen there, so we actually have our oxyhemoglobin. At the same time as oxygen's coming in and wanting to join with hemoglobin, it also triggers the carbaminohemoglobin to give up its carbon dioxide, so now hemoglobin is made available for more oxygen to come in and bind, because remember 98.5% of oxygen wants to bind with hemoglobin, so it kind of triggers the release of the reduced hemoglobin to release the proton, and of the carbaminohemoglobin to release the carbon dioxide. And the proton's released. Now the bicarbonate ion can go back in and join with that. The hemoglobin releases the carbon dioxide leaves. Now it opens up room for that hemoglobin to join with more oxygen. Okay, the reduced hemoglobin that gave up the proton, now it's available for the bicarbonate ion to come back in and join with it and form carbonic acid. Of course, the chloride will leave when the bicarbonate ion comes back in, because of when a negative charge comes in, a negative charge has to leave. If a negative charge leaves, a negative charge has to come in to keep that neutral balance of charge inside the cell. Okay, now, so here's here's carbonic acid, which came from the joining of the bicarbonate ion back with the proton. Then our enzyme, carbonic anhydrase, breaks this down into water and carbon dioxide. So now this carbon dioxide will be able to leave. And we can see that. So again, what all has happened here? Oxygen came in, caused the reduced hemoglobin to give up the proton, so oxygen can basically bond with it and form our oxyhemoglobin. Okay. The carbaminohemoglobin also gave up its carbon dioxide, because remember, we're going from a high partial pressure to a lower partial pressure of carbon dioxide. So it gives up the carbon dioxide, giving more hemoglobin for oxygen to come in and join. 1.5% of our oxygen just came in and went directly into the plasma. Okay, what else happened at the lungs? Our bicarbonate ion came in, traded places with the chloride ion. Now, when it came back in, this proton that was released allowed the bicarbonate ion to join with it to form carbonic acid, because our chemical reaction is proceeding in this direction. Our enzyme broke the carbonic acid down into the two components of it, water and carbon dioxide. Carbon dioxide was able to exit. Now, this is important.
Small amount of carbon dioxide transported in the plasma.
This is important for another reason. We're going to talk about, if you'll remember, that bicarbonate ion becomes carbonic acid, and carbonic acid is what actually breaks down right before we exhale carbon dioxide. That becomes important in understanding respiratory acidosis and alkalosis. So keep that in mind. We'll be talking about that a little bit later. Okay, this interaction where oxygen coming in causes the hemoglobin to dissociate, get rid of its proton, and causes the carbaminohemoglobin to get rid of its carbon dioxide is called the Haldane effect. So oxygen coming in triggers these chemical reactions to occur. That's the Haldane effect. Okay, so now we're unloading and loading in the tissues. Now again, unloading and loading, as I've said several times, all have to do with what's happening in the blood. What's unloading from the blood in the tissues? Well, oxygen is. What's loading into the blood at the tissues? Well, carbon dioxide is. So 7% of carbon dioxide just goes directly into the plasma. 70% of carbon dioxide goes from the tissue through the plasma into the red blood cell, where it joins water, and what catalyzes that reaction, or what allows that reaction to happen, is the carbonic anhydrase, the enzyme, puts those together, forms carbonic acid. Okay, now carbonic acid then dissociates into the proton and the bicarbonate ion, where the bicarbonate ion then shifts and it actually goes into the plasma again, trades places with the chloride ion. Okay, now notice that the hemoglobin, the oxyhemoglobin, once it gives up its oxygen, now this proton that came from the carbonic acid has a place to go. So now this proton will join with that hemoglobin and form reduced hemoglobin once the oxygen's given up. And we call that interaction between the hydrogen ion binding to this and the joining to the hemoglobin after the oxygen's given up, we call that the Bohr effect, and that occurs at the tissues.